Alright, let's go. Number 10. The Pioneer Anomaly. In 1994, JPL navigator John Anderson was just trying to keep two aging spacecraft on their books. Pioneer 10 and 11 had already done their jobs, flown past Jupiter and Saturn, and were now coasting toward interstellar space. Anderson's task was mundane: use their radio signals to refine navigation models for future missions. Standard gravity, adjusted for the sun's pull and the tiny thrust of onboard heaters, predicts exactly where a spacecraft's radio signal should land. Anderson kept getting the wrong answer. Both probes were arriving very slightly early, as if something invisible were pulling them back toward the sun. In 1998, Anderson, Michael Martin Nieto, and Slava Turishev published their findings in Physical Review Letters, and a follow-up 2002 paper in Physical Review D pinned the anomalous acceleration at 8.74 times 10 to the negative 8th centimeters per second squared, holding steady across 20 to 70 astronomical units. Engineers blamed gas leaks. Ruled out, leak rates didn't match the constant signal. They blamed uneven heat radiating off the plutonium power source. Partially confirmed by 2012, but independent reanalyses, including a 2021 paper in Progress in Physics, still find residual acceleration the thermal model doesn't fully absorb. Every spacecraft that has ever calculated your GPS position, your weather satellite's orbit, your phone's clock, relies on gravity behaving exactly as predicted. For 30 years, two probes quietly proved it doesn't, not perfectly. Was the explanation actually complete, or did we just stop looking once the discomfort became manageable? 10 years after Pioneer, the same agency found something stranger in spacecraft that were still under full control. Number 9. The Flyby Anomaly. In the 1990s, JPL engineers were tracking routine Earth gravity assist maneuvers, the slingshot trick that lets a spacecraft steal a little of a planet's orbital energy to reach its destination faster. Newtonian mechanics says a flyby conserves orbital energy relative to the planet. Whatever speed a craft gains on the way in, it should lose an identical amount on the way out. In 1998, engineer Anderson noticed the numbers for Galileo weren't balancing. Then Near joined the list, and it wasn't subtle. In a 2008 Physical Review Letters paper, Anderson, Campbell, Ekelund, Ellis, and Jordan documented that the Near spacecraft's 1998 Earth flyby left it moving 13.46 millimeters per second faster than the models allowed, with an uncertainty of just 0.13. Rosetta gained 1.8. Galileo's second flyby actually lost 4.6. 6 missions, 6 different numbers, all correlated with the spacecraft's incoming and outgoing latitude in a formula nobody could derive from first principles. Atmospheric drag was tested and dismissed. The altitudes were too high. Tidal forces, magnetic field coupling, relativistic frame dragging, all proposed. All too small by orders of magnitude by more than a factor of 1,000. Later flybys of Rosetta and Cassini, oddly, showed almost nothing, and nobody can explain why the effect seems to be fading. The machines we trust to navigate the solar system have quietly been gaining or losing energy from nowhere, and the agency that flies them still doesn't know the source. Some anomalies fade with better instruments. This one only widened as astronomers looked further out. Number 8. Flat rotation curves. In the 1960s, astronomer Vera Rubin wasn't hunting for missing matter. She and instrument builder Kent Ford were simply trying to measure how fast stars and gas clouds orbit within the Andromeda Galaxy, using spectroscopy to catch the Doppler shift of glowing emission regions. Newtonian orbital mechanics is unambiguous here, since almost all of a galaxy's visible light sits near its center. Stars farther out should orbit slower, the same way Neptune crawls compared to Mercury. Rubin and Ford measured 67 emission regions across Andromeda, from 3 to 24 kiloparsecs out. The curve should have dropped. It stayed flat. In their 1970 paper in the Astrophysical Journal, volume 159, page 379, they showed stars at the galaxy's edge orbiting just as fast as stars near the core. By 1980, Rubin, Ford, and Norbert Thonard had confirmed the same flat curve in 21 separate spiral galaxies. Measurement error was checked and rechecked across a decade of data, and held. Gas dynamics assumptions were tested against independent 21-centimeter radio observations by Morton Roberts, and they matched. The surviving explanation, invisible halos of unseen mass 5 to 10 times heavier than everything we can see, has never been directly detected in any laboratory on Earth, despite 40 years and billions of dollars in dedicated experiments. Every star map, every telescope image, every photograph you've ever looked at shows maybe 15% of what's actually out there gravitating around you. Nobody has ever held a particle of it. Rubin's missing mass sent astronomers looking for it in bigger structures. What they found didn't fit any better. Number 7. The Abell 1689 concentration problem. In the early 2000s, astronomer Tom Broadhurst's team pointed the Hubble Space Telescope at Abell 1689, one of the most massive galaxy clusters known, to map its dark matter using gravitational lensing, the bending of background light around its bulk. This was routine cataloging work meant to test how well cold dark matter simulations predict cluster structure. Standard cosmological models predict a specific relationship between a cluster's total mass and how centrally concentrated its dark matter halo should be, following what's called the Navarro-Frank-White profile. For a cluster this massive, the models expected a concentration parameter around 5. Broadhurst's 2005 analysis, using 106 multiply-lensed images of 30 background galaxies, found a concentration between 8 and 14, nearly triple the predicted value. The cluster was bending light as if its core were far denser than any simulation allowed. Line-of-sight elongation was proposed, the idea that we're viewing an ordinary halo stretched toward us by chance. Later independent studies found the same excess in multiple unrelated clusters, which elongation alone can't explain. Early formation models were floated next, suggesting these halos collapsed sooner than the standard timeline permits, which would mean rewriting when structure in the universe actually began. Our best model for how the majority of matter in the universe clumps together doesn't match observations at the scale of the largest bound structures we know. If the model is wrong about how mass concentrates at this scale, what else has it gotten wrong closer to home? The concentration problem wasn't the only thing wrong with how these clusters bend light. Number 6. The giant arc excess. Astronomers running the Sloan Bright Arc Survey were cataloging something almost decorative: the luminous, stretched arcs of background galaxies smeared across the sky by cluster gravity, useful mainly for finding new lensing clusters to study. Cold dark matter simulations make a firm prediction about how large these arcs or Einstein radii should get, based on how much mass sits at a cluster center. In 2008, Tom Broadhurst and Renan Barkana compared the observed population of giant arcs against simulated cluster catalogs, and found the real universe was producing far more oversized arcs than the models allowed. Oguri and Blanford's 2009 follow-up quantified it precisely. The standard predictions were excluded at 4 standard deviations, a result rarely dismissed as chance in physics. Triaxiality, clusters shaped like stretched footballs rather than spheres, was proposed and partially absorbed some of the discrepancy, but not all of it. Non-Gaussian primordial fluctuations were suggested next, requiring physics from the first fraction of a second after the Big Bang to already be different from the standard picture. Neither fully closes the gap even now. Light from galaxies billions of years old is arriving bent more sharply than the universe's leading model says it should be, meaning the invisible mass map astronomers use to interpret every deep field image might be subtly, systematically wrong. Not every gravitational anomaly needed a space telescope. One of the strangest ever recorded came from a pendulum in a Paris basement. Number 5. The Allais Effect. In 1954, French economist and physicist Maurice Allais was running a month-long continuous experiment with his custom-built paraconical pendulum, testing an unrelated theory about gravitational coupling with the ether. He wasn't watching the calendar. The precession of a properly isolated pendulum should be smooth and constant, purely a function of Earth's rotation, the well-understood Foucault effect, averaging about 0.19 degrees per minute in his lab. On June 30th, a partial solar eclipse crossed Paris. At the moment it began, Allais's pendulum's plane of oscillation abruptly swung by roughly 13.5 degrees, and stayed shifted for the full 2.5 hours the eclipse lasted. He repeated the observation during the 1959 eclipse and recorded a similar, if weaker, deviation mechanical interference was ruled out through his meticulously documented apparatus. Thermal drift was checked against lab temperature logs and didn't correlate. In 1970, researchers Saxel and Allen recorded comparable disruptions in an independent torsion pendulum during a different eclipse. Dozens of replication attempts since have split roughly evenly between confirming some anomaly and finding nothing at all, and no mechanism, mundane or exotic, has ever been agreed upon. Gravity is supposed to be the most reliable force in physics, silently governing your footsteps every second of your life. On a handful of afternoons, in a handful of labs, it appeared to flinch, and nobody can predict when it might happen again. If gravity can misbehave on Earth, the next question was whether it treats all matter equally. For antimatter, that had never actually been tested. Number 4. Anti-gravity antimatter. The Alpha collaboration at CERN spent 30 years just learning to make antihydrogen exist for more than a fraction of a second, trapping antiprotons and positrons in magnetic fields to keep them from touching ordinary matter and annihilating. The original goal was spectroscopy, comparing antihydrogen's light signature to hydrogen's. Along the way, they built a vertical apparatus called Alpha-G to finally settle a question left open, since antimatter's discovery in 1932, does it fall down, like everything else, or could it fall up? General relativity's equivalence principle demands it falls the same as ordinary matter, no exceptions. In their 2023 paper in Nature, volume 621, pages 716 through 722. The Alpha team released trapped antihydrogen atoms and tracked where they struck the chamber walls. About 80% of the annihilation flashes appeared below the trap's center. Antimatter fell down. Gravitational repulsion, the idea that antimatter might explain why the universe is filled with matter and almost no antimatter, was ruled out. A hypothetical fifth force carried by a massless graviphoton, raised by physicists as an alternative if the result had gone the other way, became unnecessary to invoke. But the measurement's precision was only about 20% of standard gravity, nowhere near tight enough to confirm antimatter falls at exactly the same rate as matter, only that it falls. The deeper mystery survived completely intact. If matter and antimatter are gravitationally identical, why does the observable universe contain overwhelmingly one and almost none of the other? While CERN was chasing antimatter, a decades-old rival theory to dark matter itself was quietly failing its biggest test. Number 3. The MOND divide. In 1981, physicist Mordechai Milgrom at the Weizmann Institute was trying to explain Vera Rubin's flat rotation curves without inventing an entirely new form of invisible matter. His idea, below a specific tiny acceleration threshold, Newton's second law itself bends. Add one new constant to physics, and dark matter becomes unnecessary at the galactic scale. Dark matter models, by contrast, predict gravitational behavior should scale consistently upward, from single galaxies to galaxy clusters using the same halo profile everywhere. In 1983, Milgrom published 3 consecutive papers in the Astrophysical Journal laying out the theory and its consequences, after Nature had already rejected it. For individual spiral galaxies, MOND worked astonishingly well, fitting entire rotation curves with a single free parameter. Then astronomers pointed it at galaxy clusters. In 1988, Simon White and Julianne Lee found that to fit the Coma cluster, Milgrom's universal acceleration constant needed to be roughly 4 times larger than the value that worked perfectly for galaxies. Adding 2 electron-volt sterile neutrinos was proposed to patch the cluster scale gap, and remains unconfirmed by any particle experiment. Hot X-ray gas mass was folded in as a partial fix, closing some but not all of the discrepancy. More than 40 years later, dark matter fits clusters well, but requires an undetected particle nobody has found, while MOND fits galaxies elegantly, but breaks down exactly where dark matter succeeds. 2 rival theories, decades of testing, and neither one works everywhere gravity operates. Even our most precise instruments on Earth, atomic clocks accurate to a quintillionth of a second, weren't spared from gravity's strangeness. Number 2. The millimeter redshift. At Gila in Boulder, physicist Jun Ye's team was refining strontium optical lattice clocks for practical purposes, geodesy, satellite timing, nothing to do with testing Einstein directly. General relativity predicts that a clock deeper in a gravitational well ticks slightly slower than one higher up, an effect well confirmed across distances from 30 centimeters to thousands of kilometers. Nobody expected to see it inside a single cloud of atoms barely a millimeter tall. In their 2022 paper in Nature, Bothwell, Kennedy, Epley, and colleagues pushed their clock's fractional frequency uncertainty down to 7.6 times 10 to the negative 21st, and detected a measurable difference in tick rate between the top and bottom of that single millimeter-tall strontium sample. The top of the cloud ran measurably faster than the bottom. This isn't a broken prediction, general relativity called it exactly. What it exposes is a gap nobody has closed. Quantum mechanics assumes a single sharp value of time for every particle in a system. And this experiment proved that a single quantum object can occupy a cloud of atoms spread across genuinely different rates of time simultaneously. No existing theory says how to write a wave function for a particle whose top half and bottom half are aging at different speeds. Your own head is aging, by an infinitesimal but real amount, faster than your feet every second, and physics has no framework for what that means at the quantum scale. Every anomaly on this list, from drifting spacecraft to millimeter-tall clocks, traces back to one unfinished argument between two theories that have never been reconciled. Number 1. The problem of time. In 1965, physicist Bryce DeWitt was working through John Wheeler's canonical approach to quantizing gravity, attempting to treat the geometry of space-time itself as a quantum field, the way physicists had already done for electromagnetism. It wasn't published until 1967, delayed by an unpaid grant. Quantum mechanics requires an external clock, a variable t against which every wave function evolves. General relativity treats time as just another flexible coordinate, with no special status at all. DeWitt worked through the mathematics and arrived at an equation published in Physical Review, Volume 160, page 1113, in which the total energy of the universe's wave function equals exactly 0. There is no t anywhere in it. Formally, under his own equation, the universe does not evolve. String theory attempted a fix by adding extra spatial dimensions. 5 decades on, it has never produced a testable prediction. Loop quantum gravity tried discretizing spacetime into finite chunks. It still can't reproduce ordinary general relativity in the everyday limit. By 1997, DeWitt himself said the equation bearing his name belonged, in his words, in the dustbin of history, and no successor has replaced it. Every second you feel passing, every sense that now is different from a moment ago, may be an emergent illusion built from correlations between particles. Not a fundamental feature of reality at all. Nobody currently knows why you experience time flowing in one direction, or at all. None of these 10 cases sit at the fuzzy edges of physics, in some distant unmeasured corner of the cosmos. They sit inside the equations physicists trust the most: general relativity, Newtonian mechanics, quantum theory. Tested to extraordinary precision and still coming apart at the seams the moment anyone looks closely enough. The universe isn't confused. It has been behaving exactly the same way the entire time. We're the ones still catching up. If you want to see more videos like this, click the video on screen now.